All right, let's do another hardware sort of session. I don't think I'll do these last two because looking at it, first I don't really know. This really could be interpreted in many ways, and now this will never show up on an interview. Like, is this supposed to say you encounter 2 zeros, and then for every 2 0 you see a 1, and then on that edge you assert 1, and then you wait for 1 and then 2.5 cycles, and you assert it, or is this saying I want to assert this, which will trigger this 4, and then if the 4 asserts, then you wait 2 cycles to deassert it, and then I guess you assert this if you don't see a 4, like if 3, 4, 5, I don't know, because here you don't have a symmetric case, so it's not like having a 1 does anything. Oh, I guess this is an input, so then you say if this is asserted, then you hold the value, but is it only true for 4? I don't know. And then here, I also don't really get it because it could be anything. The Q's don't really correlate to the input values, like 0, 1, 2, 3 goes like this. But if it's 0 here, then if it's 2 to 3, I'm going here, and then 0 to 3. 3 to 0, I'm like here. 2 to 3, I'm like here. Yeah. And the 3 to 3, 0 to 3, I'm like here. And then the states are not super duper clear either. So, because it's, yeah. Maybe I'll do this one just to see if it's true that I think this just says increment on every pos edge except for if A is asserted. The other one is kind of like, I don't know, it seems like if they wanted you to do something in an interview, they would just give you spec in English, right? Because then you never would have a job where it's like, hey, here's a bunch of waves, write a circuit for it. This is usually accompanied by like English. So maybe I'll just do this as the last problem on HDLBits. This goes up to 6. There's no reset, so Q equals 6. If it's 6, then it's 0, else Q plus 1. Oh, it starts at 4. So is this saying A is like correlated with 4? Because I don't really know. Okay. Sorry. Yeah. I don't know. I guess this circuit just goes to here and then stops. Like this could be so many things. Okay, anyway, it's a dumb problem. Let's do another problem that's not so dumb. So there was a problem before called packed bytes. We're gonna do the reverse of that. So packed bytes had some input of some data, and there was some data valid that goes along with it. So each data valid is a multi-hot signal that told you like which of these are actually valid. So for example, like 110100 would say, you know, the third, fifth, and the third, fifth, and sixth bytes are valid, and then you would shove it into an output data packet, right? And you would also say data val. So then you would only have this as you, if you have 8 bytes to send out, otherwise you just keep accumulating it. So this one I've already done in the previous video. I don't want to just keep doing the same problems over and over again, at least on video. Maybe off video I will just keep doing it, because I think that one has a pretty good combination of complicated like counter stuff, and then it's quite hard because then you have to have 2 counters, and then each of the 2 counters correspond to like each of the 2 variables, like namely in and out. So I think that's a pretty good problem to practice combinational logic, looping logic, shifting logic, ORing logic, and storage logic, right? So like kind of like you get to practice a lot. But let's just do something else where you now are guaranteed that this data in always has 8 bytes. And then now your output logic says data out, data out, and then also output logic whether or not and then you can say input so I'll insert like these things, and then also on a separate channel I'll say give me data enable, and then so for example if this was like 11011, then I would output 4 bytes on here. That's I guess I would unpack it. This would just be data in, or maybe 1 cycle later, some cycles later, right? And then this data out, for example, if this had like, you know, dead beef is 64. And then what you could do is say, I just want 11, let's say for simplicity, like I just want the first 2 bytes, so this, and then I want this byte. So then you would just do beef. Okay, and then lastly, you need data ready. So for example, data ready says to back pressure the input channel. So this is just saying, yeah, I'm not going to accept any of this. So don't expect me to get any of this. And the reason is because suppose you have dead beef, so 64 bytes of data, and you want to output this kind of 1 byte at a time. Oh, actually, sorry, in the previous example, this would be dead beef. So you would serially read what you have, and then you would just fragment it. Yeah, this makes more sense. So here you would unload this, and then you only have like this data left. But as long as you have some data left in your internal buffer, you can't have this. So this is just basically saying internal buffer isn't empty. This is tricky because for cases of all zeros, you can't just say internal buffer is equals 0. You have to consider all zeros here. And if it's all zeros, you don't want it to be aliased with data ready. Or maybe you can actually, because then your output's always zeros. So I don't know. So we're gonna implement this unpack bytes here, and 35 minutes to do it. I might not test it out per se. We'll see. Input, clock, reset end, and then I'll also input so let's work backwards, right? And this is a fairly difficult problem. So if we have data in, we need to store it to memory. So I need some sort of memory to be able to store things in. And then I also need, well, we can just maybe work backwards. So what is data out, right? And what is data val? And so data out is reading from data in, is a function of data in. And I would say for int I is 0, I is less than 8. I would say something like data out is of I is if data in is asserted, and this is if I want it to be the same cycle. If it's next cycle, then this would be like next data out, and I can flop it. Let's deal with that later though. So, and memory of J. If if data in of I, well, I can also just say J equals data in of I. So if I've read something, so for example like this, then I would move, so this is packed, right? Then do this. So for example, 1101, let's walk through it. Data out would have the 0th byte and then the first byte, and then J would increase. So once you have the 0th byte, then this would go to 1, and then you add the first byte. This wouldn't trigger this, but data out for it will also be 0. And then, but then after this, J equals 2. So then we would read the 3rd byte of the memory here, and then the 4th byte here. And if it's zeros, then the rest is all good. Anyway, typo here. If data in, then I increment J. If data is not in, then we don't need to read the next byte. And then let's do async reset or negage. Then first like this. If data in is all zeros, if data n and data n is different. My bad. Data n is this one. Data in is this one. Okay, so data enable. So if it's enabled, then J would increase, and if data is not enabled, J just remains the same. We keep scanning. Coolio. So the other thing I needed to handle is, let's say J ended at 0, 1, 2, 3, then my memory needs to shift to the right by how much? J plus 1. This is the tricky thing because J is 0 and then J is, well, if I do this, then J is 1. So actually I would trigger this 4 times, so this would J end at 4. So then I actually just need this, which makes sense. So if J is, so if there's no enable, J ends up at 0, I don't shift it by anything. But if J is 1, then, let's say I read at 1 byte, then I want to shift right by 1 byte. Okay. you probably want to have something with like bytes remaining. And if data is valid and data is ready, then actually this needs to go to a place where data not ready. Because we only do this if the buffer isn't empty, right? So we have a handshake, then let's shift in the data in to memory. And data ready is no longer ready. And bytes remaining is simply going to be 8. Actually, this is fit in 1004, so actually we need this. 1000 is 8, so anyway, this is saying like input channel handshake, shift in data and reset bytes remaining. And then this kind of falls out of how this is implemented, but the original intent is like if you only have 1 byte left and you have this, like 1 byte left in your memory buffer and you have like this 4, then yeah, it's fine to just output zeros. So if I shifted out 4 bytes, then the remaining for the next cycle is 4, and then let's say I do like another one where this pop count is 1, then J would just go to 1, and then you shift up by 1, and then you just do this. So what I want to do is I don't want to deal with negative numbers. So if J is greater than or equal to bytes remain like this, then I just want to output this. Data ready is singular, this is fine, this is data in, this is not ready, and then this gets reset to 4.8, and this gets shifted to the right by J bytes. And if the number of bytes we're reading out is, number of bytes we're reading out is J, so we get rid of it. And then if the number of bytes we're reading out is actually greater than or equal to the bytes remaining, we have 0 bytes remaining. Otherwise, we have bytes remaining minus J, which is always guaranteed to be a positive number because of this. And then let me do this actually. Bytes remaining next, assign bytes remaining next equals this. And then so this is just bytes remaining next. And then I wanted my data ready here to just basically say if this is equals 0, Makes sense. So this is my data out, and this is my data enable that controls this. And then data valid. If data out is the same as this cycle, I can just say assign data val equals data enable. Not a trick question, I just didn't know it when I designed the question. And so we've handled this situation, which is just this pass through, and it's in the same cycle because data enable can immediately get data out by just reading what's inside the memory. Actually, this is a little trickier because you need, what you're gonna need is also that I actually read in something, because if I actually don't have anything read into memory, meaning, I mean, this 8 is shifted in at the same time this data is shifted in, right? So you can say, well, if this is 8, then this is also readable. You can't just check 8 because 8 is the full buffer. So as long as if this is like non-zero, then if this is non-zero, you have some data to read, and then your data in is just gonna be qualified by this. So for example, if I never shifted in anything, data in able would be 0 because my bytes remaining is actually 0, just nothing to read out. So this would go to a 0, and then the entire 8-bit bus goes to 0, and then this goes to 0. So this is handled, this data out is handled scanning from the memory. This data enable is used to scan the memory. Output ready is used where it's always going to be ready at the beginning of time, and then if I have a handshake, I'll deassert ready and I'll reassert ready again when I have no more bytes remaining to read in the memory buffer. And then the memory is used, of course, when you scan the memory, but then the memory is also reset to nothing. And then when you have a handshake and like you're ready and data valid, then data in is in this mem. And if you're not data ready, you're just going to ignore anything that's coming in the input channel anyway, and you're just going to right shift based on how many bytes you've read out. Where here. And then, yeah, so that's how data ready. Oh, so data ready, and then data ready is 0 because we're waiting for stuff to read. And then, but then if you finish reading it, data ready reasserts again, and we're ready for the next request. Is how's data val used? Data val is used somewhere. Okay, I probably should do that. So data val is just used here, right? Because data val just says, hey, I want to shove this data in to your internal memory buffer. And this is all this does, qualified with ready. If it's not ready, just ignore it. And then this data in is, of course, just going to be shoved in the memory buffer. Let's see if this compiles. So I think this is somewhat complete in the sense of, okay, never mind. It's not even Bytes mem. Yeah. Okay, let's see what's next in terms of typos. Yeah, there's still 17.5 minutes left, so why don't we just play around with this? Data in, data val, data ready. I really should say data in val, data in ready. But the problem is I'm not the interviewer and I'm too lazy to substitute it. So just logic, data out and logic, data out val. Okay. And then bytes. Clock, reset n, and I should zoom in more because I think some folks can't see it. So this solution, and then data in, data val, data ready. So and then the data enable to scan the memory, and then the data out that will give in the same cycle, and then the data out val like so. Clock is 0, reset n is 1, and I'll just say go, and task of go, and task has this beginning and wrapper, and then we'll just say clock is not clock, clock is not clock. I wanna if I set something and I do it, maybe I just want to wait like 2, and then I want to do my display of something, blah blah blah, and then do this, and then do this. So what do I want to display? My bad on that, and then data ready, and I know what the data enable is gonna be like. I just guess this is also gonna be data out and data out val, which is also an H, which is actually just this by qualifier. So this allows me to reset stuff, and then this allows me to not reset stuff. And when I don't reset stuff, I'll just do one cycle of not reset stuff. And well, no, let's just straight up do data enable something like this, and my expected value for the second one should have no data out val is all I care about. And then data in is 0, and then I just want to do now data in and data val. Data in ready is same cycle, next cycle, yeah. That's fine. Data in equals dead beef, and then so one cycle read zeros, yeah, one cycle write, 0 cycle read, and then I'll say the data val is not asserted. So this should do nothing. Do nothing. Oh, I need to do stuff here. Data in data val and data ready. That's the input channel, and then data out val, and okay, this clock. So this just clocks. This is just test the front end. I just want to see if it matches my expectations. This one doesn't matter. The second one, I just care about no data out val. Great. And then this one will do nothing on this one, and then val is 1, but so here I wanted to see not ready in the next cycle. So why isn't that? So val and ready are both 1. So then bytes rem is 8. Bytes rem is 8. This should not be true. Should be 0, right, for J? And then 8 minus this is, unless I'm missing a byte somewhere, like maybe I'll look at bytes remaining and this. So I of UB and I of UB. Okay, that's interesting. So despite this being true, the data in 8 isn't clocked into bytes remaining. Unless there's some, no, they're both 1 bit. D and val, D and ready is the second and third. Yep. I don't think that'll change anything, but it will just alleviate some concerns. So So I do this, and I'm here. Reset 0. Yeah, resets 0. So resets 0. Oh shit. All right. All right, cool. So B remaining is 8 for next, and it should no longer be ready. And then so let's maybe try to spam this with maybe 1, 3, 2, 1, something like this with data enable. What other params am I changing? This just scans memory and everything's taken care of. So, you know, if as a consumer, I can see that if it's not ready, then obviously there's some data to scan. So now I can say, so in the real system, you can say, well, it's not ready. So data enable is three, and then like maybe like if, and then like something like that, and then data enable is like let's say 2, and then so beef is my guess, and then data enable is 1, 2, 3, 4. Actually, how much is a byte? 1 byte, and then 3 bytes, and then 2 bytes. So this is this beef, and then we just say, ah, okay, screw it. Should be all zeros followed by dead. So we left off at this cycle, and this looks right because we're just doing this. And did we have EF on this byte, 1, 2 byte, and then we're gonna hit it for 3, so like this. So then you have dead B. So is it dead B? It is dead B. And yeah, looks good for those bytes. And then you have, where is it? 2 more for here. So I have beef for this and this. And then I have all zeros followed by dead. So I mean, this looks great. And what I'm expecting here is on the next cycle, it'll go ahead and have a ready again. And then by the next, another cycle, it will not have ready again because my input is, I never deasserted my input. Yeah, so yeah, this is working perfectly. So because I have this zoomed in, I have like 2 minutes to burn, I'll just kind of go through sort of like every input and how it's used again, and every output how it's used. So for the input channel, this data in is going to be clocked to memory, and that is just going to be qualified by this data valid from the inputs perspective side, but our data ready also needs to handshake it to shove this data into the memory. And then this data ready is simply going to be if there's no more bytes in the buffer, meaning there's nothing to read, so don't read it. And then the input here, data enable, is just something that you use to scan this memory. And because we're fragmenting the memory to scan, we're going to scan the entirety of the data enable, because this data enable is really a multi-hot scan request, where the data enable says how is the output going to be formatted. So then the data out is all, of course, going to mirror this. And then we're going to end it with memory of J. And we don't do memory of I because, memory is packed, whereas this is defragmented. So memory J stays the same. If this particular byte isn't requested to show up on the data bus here, and if it is showing up on the data bus, then we move on to the next byte of memory to shove into a corresponding byte on the data out bus. So that's how data ready and data out and data input is used. And then what else? Data out valid is simply going to be our data enable, because that's what we're requesting, with the exception that if our buffer is empty and we're trying to read it, then we would have a situation where what? Yeah. Our data out is still 0. Even though our data enable is 100011, we see that the data out is 0, right? Because if there's nothing to read, then we can't say it's valid here. Oh, actually, I guess I don't care about data out. I care about data valid. My bad. And then also the data valid here should just match what I have for this. So as you can see, this is 20, this is 98, this is 41, and this is FF. And then nothing will be valid because this is empty. And nothing is valid here also, despite this being non-zero, right? So we know that this qualifier works, where basically if our internal buffer is empty, then there's no output data valid. So that explains, how this is derived, and our data ready just looks at this. And then this explaining this part, which is like the only part that I think I haven't explained yet, bytes remaining next. Bytes remaining next just says how many bytes of data are you reading and therefore shifting out into existence. If this number of bytes you're shifting out is bigger or equal to the data that you have left in number of bytes remaining in your buffer, then you don't have any bytes remaining in your buffer, which would also trigger this in the next cycle, this data ready. But if the bytes remaining is bigger than the number of bytes you'd like to read out, then your bytes remaining next is just simply going to be the difference of what's remaining in this cycle versus what you actually read out this cycle, right? So I mean, that's it for this video. This was surprisingly very few bugs. I guess a lot of practice going very slow and then kind of talking my way through does help a bit, except for that silly reset inversion.